Okay, I think it's going.
All right. Okay, everyone. So thanks so much for coming to our first professor lecture of the Sumo Speaker Series. Today we're very lucky to have Rick Sommer here with us. Rick works in the Stanford Department in Set Theory and Logic. He started the SUMAC program, which is one of the most sort of successful and prestigious summer math programs for high schoolers in the country. And he teaches a variety of set theory and logic classes here during the year. Today he will be giving a talk on proving independence. And so without, further ado, I'll hand it over to him.
Thank you, Arden. And very happy to be here, excited to talk to all of you. Thank you for the introduction. Yes, I'm interested in logic and set theory. I'm a curious person. I like to think deeply about whatever I do. And I'm passionate about doing mathematics. I like to think deeply about mathematical practice and think about what is mathematical practice, what are the powers and limitations of mathematical practice. And that was what led me into studying logic as an undergraduate, graduate student, and then continuing to do research in it and think about it. So yeah, that's my motivation. And in the various branches of logic, that's a kind of a theme, is studying the power and limitations of mathematical practice. Before I go much further, we should think about what is mathematical practice. For me, the way I think about it is mathematicians like yourselves, have this world of mathematical structures or mathematical objects that you study, and in order to understand them more deeply, you want to prove facts about them. So you have some formal mechanism for proving theorems, and that begins with some basic assumptions, namely axioms, that lead to, through logical reasoning, to proofs, and then ultimately to theorems. So here's the basic idea of mathematical practice. And when I speak about mathematical structures, I can think about the study of mathematical structures, and by that I mean things like, mathematical structures define the different branches of mathematics. So you think about, in number theory, the mathematical structures you study are, say, the integers with operations like addition and multiplication and various relations. In calculus or in real analysis, you're studying continuous functions on the real line. You're looking at operations like differentiation and integration. If you think about set theory, obviously we study sets, etc. Right? And it's the same thing in the sciences. The different branches are defined by their objects of study. In biology, you study biological objects, etc. So we study, it's the study of mathematical objects, or if you want, mathematical structures. And when I think of, I'll use the terminology here also, models, and that comes from logic. I meant to ask at the beginning, who has taken full 151, philosophy 151? That's all good. No background in logic is required, but I was just curious. Using proof from axioms to theorems. And these are the components of, to some extent, of mathematical logic. There's a branch of mathematical logic called proof theory, where we want to understand the proof part of it. There's a branch of mathematical logic called model theory, where we want to understand what's going on generally in the case of models. There's a branch of mathematical logic called set theory, where we try to dig into the axioms that might be sufficient to prove everything in mathematics. So it's all of these are kind of foundational questions. Computation is also part of mathematical logic, so there's another branch associated with that. I'm not going to give you the whole breakdown of the different branches of mathematics, but I wanted to get some of these ideas forward. And so there's this idea of going from axioms to theorems, and then again you have these models and combined structures. Just some examples that I want to explore today. I'm going to look at three. So these would be, first of all, the branch of mathematics, if you will. The kind of the theory. Well, let me add something. I want to say what a theory is, because we use that term quite a bit. A theory equals all theorems provable from a set of axioms.
Now, the idea with the axioms is that these are sometimes referred to as self-evident statements about our mathematical structures that do not require proof. If you think about it not even deeply, but just at all, you think about, well, a proof is logical reasoning from some known things to other known things, and you have to start somewhere. The axioms is your starting point. And if I take A as a set of axioms, and I'll give some examples in a moment, I'll sometimes write T of A, or sometimes T sub A, these two different notations for the same thing, to be all theorems, everything that follows logically from those axioms. Okay. And so some examples of the theories. So theories, you can also think of branches of mathematics as corresponding to theories. So if I want, you can take my example I mentioned a moment ago, number theory. And there's a famous set of axioms for this. You don't need to know this in detail, but they're due to piano. So there's the piano axioms. And basically what these are is induction together with basic facts about plus and times, using plus in two different ways. Piano axioms are really quite simple. And supposedly everything you do in number theory follows from, well, you know, which, like if you take Math 152, in theory, they can all be formalized in piano arithmetic. And then if I look at models or structures, they have several components. One would be a universe. Those are like where the objects of study live. And then the other piece will be things like functions and relations on that universe. So if you study number theory, you're studying the integers, and your functions and relations are things like plus and times. Right? So when I refer to a model, I'm thinking about that context. Again, the mathematician, number theorist, is looking deeply at these things, trying to prove facts. Maybe most number theorists don't really think about piano's axioms, but in principle, everything could be there. That could be a start. And feel free to ask questions. A second example is geometry. This is like a much older one, and more famous. There, the axioms, the Euclid axioms. That's one example. There are more modern axiomatizations of geometry, but this is the one I want to look at. The universe could be the Euclidean plane. I'll call it R2, just simply a plane. Or you could take the universe to be geometric objects. Like I said, different branches of mathematics are determined by their objects of study. So you can say, lines, points, circles, triangles, whatever else. And then the functions and relations are things like congruence or similarity or parallel, whatever else. Right? So we have these different relationships that we use in geometry. All right, so those are the ones at hand. Now, let's see. Oh, and I'll say like one other kind of definition that I want to throw in here is true statements are statements that hold in the intended model. So these, I have my third one on here. I left room for it. I have to fill that in. True statements are statements that hold in the intended model. So like we can think about like a true statement in number theory might be something like infinitely many primes or Fermat's last theorem or whatever it is, and we're saying, well, that holds in the integers with plus and times. Or in Euclid's case, I mean, in geometry case, we can say, no, a true statement would be like the side angle side theorem, whatever you might remember from your geometry days, and you can say, well, that holds in the plane. My last example, which will be one of my most important ones, is set theory. And here the axioms at hand, Zermelo Frankel is a pair of names that provide a list of axioms, which I won't give you, but I'll be making reference to it. Sometimes this is called CF. And these are axioms that date back over 100 years. And they capture intuitions about a universe of sets. And so I'll say that the universe of sets that I'm thinking about is what we refer to as the cumulative hierarchy of sets. might have to define that a little bit further later on. But if you start with nothing, and then you produce your first set that you can get from nothing would be the empty set. So start with the empty set, and then you build up from there. The basic operation of building up would be taking subsets of things. And so I'll just say taking subsets of existing sets and going on forever. I'm gonna say dot 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 here, just as a way to continue. And like I said, I might have to describe this in more detail later on, just to provide some clarity. But set theorists work in a world of pure set theory, meaning that they don't introduce any other objects like the integers or the reals. They define them in the context of set theory. Take my math 161. You know what I mean? That means that's offered in the spring. I didn't. That's a little plug there. But in any case, there's a kind of an imagined universe of sets that set theorists think about. And I'll point out that there's a lot of clarity on what the integers are. People know the integers pretty well. You know, these are friendly mathematical objects we encounter every day, and we have like a lot of confidence about truth in this space. And same thing with geometry to some extent. You know, we can imagine the plane, we can think about properties of points and lines and circles, etc. But in the case of set theory, things get to be a little bit more vague and less tangible, as I'll point out. But we still think we have like a pretty good idea about truth in set theory, and we can kind of use our axioms to prove theorems that we think are valid in this model, in this universe of sets that's being described. Okay, any questions? That was kind of my opening. I'm going to run out of board space pretty soon, and I'll have to have an eraser ready. But what I want to next get to is that a big, like startling result of mathematical logic from just under 100 years ago was due to Gödel and Gödel's Incompleteness Theorems. And so in particular, there's something called Gödel's First Incompleteness Theorem that says that our system that I described over there, going from axioms to theorems, is flawed in a way, where it's deficient or it's not going to necessarily give us everything we want. And in particular, it's going to come short of being able to prove everything that's true. And it's a fundamental issue. It's not that we haven't come up with sufficient axioms to do that, or it's not a flaw in our logical reasoning. It's sort of inherent in our activity that we are not going to be able to prove everything that's true. And in fact, one way of framing this would be that given any reasonable set of axioms for a theory, and it could be any of these theories over here, and reasonable I won't define, but things like we should be able to tell if an axiom is an axiom. It should also be the case that some basic facts about whatever objects, numbers, in the case of number theory, are provable. So given a reasonable set of axioms, there are statements neither provable nor disprovable. And these are called independent statements. So they're statements neither provable nor disprovable. I'll say refutable sometimes, but in this instance, and therefore, you can conclude from that there are true things that you can't prove. So there are true facts that are true statements that are unprovable. That's because you expect that given any statement, it's either true or false. And so if it's neither provable nor disprovable, one of those is true. And so the one that's true is not provable. Okay. You good up to that? Right question.
Is this like a finite set of axioms?
So-
Like whole statement or
Yeah, so the set doesn't need to be finite. And in fact, in the case of these over here, I mean, in particular for the axioms of number theory, I mean, piano axioms are infinitely many induction axioms, as an example. But I said reasonable means that you have to be able to tell when something's an axiom or not. So for example, you said, I want my axioms to be all true theorems, you would need to have a test to see if a theorem was true, a statement was true. And the claim is that our method of testing whether something's true, which is finding a proof for it, is not going to give us all the true statements. Right? So in the end, another conclusion from this is that the true statements of a theory, the theories that are written down, are undecidable. There isn't a decision procedure that allows you to test whether something's true or not. And that makes it so that the proposed axioms being all the true statements won't work. That's unreasonable in the sense I can't tell if something's an axiom. So I have to be able to describe the axioms in a way where somebody can formally test that. And it has to be computable, decidable, recursive is a word that logicians use for that. Okay, good question. Thank you. I encourage questions. All right, so the question, so these things are called independent. So these are independent statements. And so there are lots of questions come out with this. Right? So one thing would be, is there anything that we know to be independent of the axioms? It's in some sense unprovable. It's true statements that are unprovable, or statements that we can't decide whether they're true or false. I mean, you can pick open problems off of somebody's list, and you can say, are these problems potentially problems that we're not going to be able to resolve using our standard methods of mathematical practice? And what are the implications of that? What kind of limitations? So this is, I'll say more on this, and this is what I want to share with you today. This is like how this works and what kinds of statements fall in this category. I'll point out that Gödel's proof of this involved the following. He came up with a way of code. So he worked in number theory, so in piano arithmetic. I'll abbreviate that this way. Just make sure we have that right here so you know what I'm referencing. But in piano arithmetic, he found a nice way of using numbers to code syntactic objects. And by syntactic objects, I mean statements, proofs, etc. And so that he found a way to use statements of number theory to talk about proofs. So you can come up with a statement that describes whether or not a proof exists or not. So within PA, there is a statement, sigma, and I could say for any theory that's a reasonable one, by the description that I was alluding to up here, there is a statement, sigma, that expresses sigma is not provable. In other words, it expresses it's not the case there exists an n such that n codes a proof of m. So remember, just a second ago I said he came up with a way of coding statements as numbers. So he and proofs as numbers. So n here is referencing the candidate proof. He says it's not there's a statement that expresses it's not the case that n codes a proof of m, where m equals the code of sigma. So basically, sigma expresses I am not provable. This is analogous to the liar paradox, if you're familiar with that, where if I say I am not a liar, or I am a liar, then you can't believe what I just said, and so I must be telling the truth, which means I'm a liar, and therefore what I just said is true, which means I'm a liar, so you can't believe it, and you get into this kind of circular thing. But this happens in this very formal way. So this statement is either, like you want to test to see if you can prove it. It turns out that his system of formalizing mathematics and number theory works so well that if you can prove this, then it's really the case that there is no proof. Right? So if you prove this, the fact that there's no code of a proof says that you really can't prove it. So that tells you you can't prove it. If you can't prove it, it's true. You should notice that. Which means that you don't really want to be able to disprove it. But suppose you could disprove it, then that would mean that you're proving the negation of it. That would say that there exists a proof of it. So if you disprove it, you actually prove that you prove it. And so that contradiction says you can either prove it or disprove it. So that's an example of an independent statement. It's neither provable nor disprovable, but it's true. Okay. And that was like the first example of this kind. Now I'll point out, it's not the first example of an independent statement, but it is the first example that where you had this kind of construction that said any reasonable set of axioms you can do this. Okay. And in that, you know, your question about like, are these finite or why can't you know, like what are the limitations here? You need to be able to have a statement in the language of piano arithmetic that expresses something follows from a set of axioms. And in order to do that, those axioms you have to have a handle on. You have to be able to describe them kind of mathematically. Okay, so that's all my lead-in. Now I'm going to look at my examples, and given I'm out of board space, I'm going to have to read some things. So you have to just remember what models and structures and proofs are. I'm going to leave this part up here. Well, before I give my examples, I want to point out, like, you know, I named some questions here, but you know, one is like, are there familiar statements that are neither provable nor disprovable? What does that mean? What are the implications of that? But you could also say, well, and this is what a lot of people did. They said, oh, Gödel came up with this clever trick and came up with this kind of, like, it's often referred to as a mathematically motivated, meta-mathematically motivated statement. I mean, number theorists don't care about statements that talk about codes of proofs. You know, number theorists care about interesting properties of the integers. And so this isn't something that number theorists would be interested in because it's meta-mathematical, as we say. So the question is are there mathematical examples? And I'll go through each of these. I'll start off with this one. And I'll say the answer is yes. And so for number theory, there are, since like the late 70s, and I'm a pretty old guy. I started my undergraduate, I don't necessarily want to reveal how old I really am, but I was a grad student in the 80s, right? So it wasn't very much earlier than I became a grad student that some of the first really interesting mathematical examples came up here. So in number theory, there are combinatorial statements that are independent of piano arithmetic, and I'll say that some are similar to Ramsey's theorem. So if you're familiar with Ramsey's theorem, which can be framed as well, there's some finite, nice finite examples. Any group of 6 people, there are either 3 people that are mutual friends or 3 people that are mutual strangers. That can be expressed mathematically, and you can extend that to an arbitrary size group of people. And there's a statement similar to that. Now, if this statement was not discovered by number theorists, this one that's similar to Ramsey's theorem, it was discovered by logicians, Paris and Harrington. And Harrington was somebody at the faculty at Berkeley that I learned a lot from. But they did this in 1977. And I'm not going to give this example now, but I just want you to know that there's some kind of interesting things that logicians came up with that have the flavor of what a number theorist would come up with, but did not come right out of number theory. So, maybe that's not too exciting. There's some other examples of sequences of numbers that you raise the question, does this converge to a particular number? Does it go off into infinity? There's one due to Goodstein. That's like a beautiful result that is independent of piano arithmetic, meaning you can't prove it, can't disprove it. For both of these, people think they're true. I mean, they have proofs of them in set theory, so that we've kind of validated them, independent of our usual axioms of number theory, but still not quite, like rock solid. This is something that number theorists would care about. But in geometry, the story's a bit different. I could have started with the story of geometry, and this one predates Gödel, predates a lot of folks. But in geometry, if we look at Euclid's axiom, there's the question of, I'm going to, I think I want to pause before I give the geometry example and just erase this here for a second. I want to point out that there's something I skipped, which is the method for showing things are not proven or not a better independent. So I'm going to come back to geometry in a second, and geometry will be a demonstration. So methods of showing independence. Check time real quick. So methods of showing independence. So if you want to show something is not provable, one way to do it is like find a counterexample, or if you want to prove it's the opposite. So showing something is not provable, it's pretty standard ways of doing that. However, if you show something is not provable by proving the opposite, then it's not going to be independent. Because in the case of an independent statement, both the statement and the opposite can be provable. So showing something is independent needs to be more clever than that. You have to come up with some interesting ideas. This is related, the methods, one of the main methods is actually something that comes out of earlier work of Gödel related to the fact that Gödel showed that our logical framework for proving facts in mathematics is, as we use the terminology we use in. So this is, I'm going to use the word complete here, but I'm actually going to put the word logical in front of that. Logically complete, which is in contrast to mathematically incomplete. So in the one case, I'm referring to a logical completeness. In the other case, I'm referring to a deficiency in our system. And so I don't need to confuse you with using kind of complete in two different ways, but the point here is that the mathematical completeness comes from a deficiency of our axioms in being able to fully characterize the truth in our models. The logically complete is a good thing. It says that our method of proving will always capture logical validity. So Gödel showed this in around 1929, and it says our formal framework captures logical validity. And I'm not going to define logical validity formally here, but it's saying that if we want to, there's a corollary to this, which is going to say that if we want to show something is not provable, it's sufficient to show that there's a structure in which that statement is not valid or false. So I'll say it this way. To show a statement sigma is not provable from some axioms, let's say from A, it's sufficient to find a model of A in which the statement is false. A model of A, meaning that axioms of A are true, and for which sigma is false. Okay, so this will be something I'm going to illustrate in my next example. And so this means that to show something's independent, we're really looking for two models. One where sigma is true, and one where its negation is true. So independent, if M and M prime, I'll say, is two models, in one sigma, and the other not sigma. Okay, so this will be illustrated in my next example. Maybe if you're following, you might actually this might be a big hint of what my next example is going to be, especially since it says it's geometry. But the idea would be that if I want to show something's independent, I find a model of the axioms where it's true and a model of the axioms where it's false. Well, in number theory, it's hard for us to imagine models other than this one. Right? So that's part of what makes number theory hard is if you think about piano axioms, they describe this. But here's an interesting thing about logic, a result of logic, and it's related to that completeness theorem. Is it turns out there will be other models that satisfy the axioms. that's like above the scope of this talk, so I'm not going to go in that direction. But if we come to geometry, we actually end up with a really interesting example. So in geometry, from the very beginning, Euclid, well, not the beginning, but if we go back a couple of thousand years ago, Euclid laid out an axiom framework for geometry that has persisted for like 2,000 years, that in which there was a question raised about one of his axioms. So the question was, is the parallel postulate provable from the other axioms? Sometimes the axioms without so the parallel postulate, just to remind you, in case, and I'll point out that the thing we call the parallel postulate in Euclid's books is not really what I'm describing here, it's the variation of it that implies this. But the parallel postulate says, given a line L and a point P, not on L, there is exactly one line that goes through P that does not intersect L. And we call that a parallel line. So you can think of it's the existence of a parallel line in that scenario. And sometimes the other axioms are called neutral geometry. Just to leave off this postulate. So people were curious, like, can you prove this? And for a couple thousand years, people tried to prove the parallel postulate from the other axioms and were not successful. Then in the late 19th century, there were some discoveries made, you're familiar, mathematicians discovered, let's say in the late 1800s, spherical geometry and hyperbolic geometry. So in one case, it's geometry on a sphere, and in spherical geometry, there are no parallel lines. So this one here would be no parallel lines. And hyperbolic geometry would be one where there are lots of parallel lines. So it's a variation of this axiom. The fact that, and if you want, in this geometry, which we refer to as Euclidean geometry, there's exactly one line parallel to L. So what this shows you in this context over here, my statement sigma is the parallel postulate. It is valid in Euclidean geometry. So Euclidean geometry is a model of the parallel postulate as well as the other axioms, which I was referring to as neutral geometry. The models of spherical geometry are satisfy the neutral geometry axioms and the negation of this axiom. Right? So this axiom is false in spherical geometry. It's also false in hyperbolic geometry. So these are two models, if you will, where the parallel postulate is false. So by demonstrating that, I find an example in in geometry of an independent statement. It's not provable from the remaining axioms of Euclid, and it's not disprovable from the remaining axioms of Euclid, because I can find a model where the remaining axioms of Euclid are true, and another model, where that statement is true, and another model where that statement is false. Okay, are we good with that? So that's my lead in to this method. And I'll point out there are a bunch of other methods for proving incompleteness in general. This one has a lot of power to it. Again, the idea is we find one model where things are true, one model where things are false. And again, I'll admit that here it's hard to imagine, but if you take a course like Phil 151, it's another course I'm teaching in the winter, then you'll actually see exactly what that means. You'll see that there are many, many models of number theory that satisfy not just the axioms, there are many models of true number theory. In other words, if we take all the true statements, the integers and plus and times as we know them are not the only model in that set. Okay, that's not meant to confuse you, but meant to be an interesting side note before I go to my next set of examples. So in that realm of like, are there statements that mathematicians care about that are independent of some axiom system? We could look at lists of problems that mathematicians care about. If you were to do this today, you might look at the Clay Millennium Prize problems. If you're familiar with those, there's 7 of these problems. 1 has been solved, the other 6 remain open. They include things like the P versus NP problem and the Riemann hypothesis and a few others. You can say, well, I wonder if any of those are independent, meaning that our methods of mathematical proof are not going to succeed in solving those problems. I mean, there are all these folks, lots of them in this building, grinding away trying to prove these things. And maybe it's like gonna never reach a net, maybe they're not gonna actually be able to do it because the methods that we're using in mathematics are not sufficient to settle those questions. Okay? So that would be an unfortunate situation. Well, if we go back 100 years prior to when the Millennium Prize problems, yes, a lot of you were born in 2000, but the Millennium Prize problems were announced in the year 2000. It was a version of something that had happened 100 years earlier. David Hilbert, really famous late 19th century, early 20th century, in the year 1900, and many of you might know this, he announced 23 open problems for the mathematical community to think about. And these were meant to be like the problems that are the most significant problems of the day, and was taken very seriously. Problem number 1 was the continuum hypothesis. And the continuum hypothesis is a problem in set theory that says the following. So I'm not going to list all 23. I'm putting a blank. How many of you are familiar with the continuum hypothesis? How many of you know about infinite cardinality? How many of you have seen a proof that the cardinality of a set of real numbers is greater than the cardinality of the sets of natural numbers? Almost all of you, but not quite. That's fine. The continuum hypothesis is about the size of the set of the real numbers. And one way of framing it is it says that I'm going to use bars around a set to indicate its cardinality, or the number of elements in a set. So this is the number of real numbers. I'm going to say this equals the next infinity after the size of the, I'll say, positive integers. So, well, I'm going to use my usual notation. I'll say the natural numbers, and this for me, and this position is include 0. So this set is clearly infinite. This set is a bigger infinite. Cantor's famous work showed that the size of the set is strictly bigger than the size of that set. And then Cantor came up with something he called the continuum hypothesis, which stated that this is the next infinity after this. This was this exploration of different sizes of infinity was a very active area of mathematical interest and research in the late 19th century and the early 20th century. David Hilbert was fascinated by this. He thought this was like some of the coolest stuff around. The fact that there are more reals than these, and there were a bunch of other things that Cantor came up with that just kind of blew people's minds. Cantor thought, well, this seems like it's probably the next infinity after this, but he wasn't able to prove it. Hilbert said, let's make that problem number 1. Just a little bit more background on this. We say that the two sets have the same size, so I'll just say like x and y have the same size if there is a bijection between them. And just to make this more interesting, I'm going to point out that the size of the natural numbers is the same as the size of the integers, is the same as the size of the rationals, but we get something definitely bigger for reals. And again, the assertion is there's nothing in between. The continuum hypothesis says there's nothing in between. In 1940, our friend Kurt Gödel, whose name has come up several times now, proved that the continuum hypothesis cannot be refuted. So, you can't prove the negation of the continuum hypothesis. And the way he did this, and depending on, I might end soon and leave time for questions, but if you're curious, I can say more about how he did this, which was he came up with a model of set theory. So I'll say can't prove in set theory, so I'll say in CF. He came up with a model of set theory in which the continuum hypothesis is true. So he found something that makes the continuum hypothesis true. Model of set theory, I'll say model of CF, in which CH holds. And that, okay, that's maybe a positive thing for Cantor because that helps support the idea that Cantor was correct with his conjecture, but it doesn't establish it because it's not a proof. It's just a proof that you can't refute it. You can't prove the negation. Then, in 1963, a Stanford mathematician named Paul Cohen proved you can't prove the continuum hypothesis. So I'll say CH is not provable from the axioms of Sommer. And so that means the continuum hypothesis is independent. It's neither provable nor disprovable. The impact of this is maybe bigger than it appears. If you're not familiar with CF, you don't know about the power of this axiom system. It turns out that CF is capable, the axioms of set theory are capable of formalizing most of mathematical activity. I mean, if I go around this building and look at what people are working on, for the most part, it can be formalized in Zermelo-Frankel set theory. What I mean by that is you can represent number systems, you can represent functions, you can represent topological spaces and manifolds, and all the mathematical objects that people around here play around with can be represented as sets, and the axioms of set theory are capable of proving the theorems that folks are coming up with in those different branches of mathematics. So for example, Zermelo-Frankel set theory proves the Euclid's axioms and the piano axioms, and proves the axioms of real analysis, etc. So what we're saying is that in this very powerful axiom system that captures most of the mathematical activity that takes place in the mathematical community, is not capable of proving or disproving the continuum hypothesis. And in fact, Cohen's work showed that there are models where the size of the continuum can be a wide range of possibilities. He showed that you can find a model where the size of the real numbers is not the next one after the size of the naturals, but one after that, or two after that, or 100 after that, or even infinite ordinal distance after that. So he proved that it was a very broad kind of thing. And this led to a lot of other work in set theory that has given us lots of other independence results. I'll name one other one. The same two characters in the same two proofs also showed that the axiom of choice is independent. And the reason I want to make note of that before I conclude is that in the case of the continuum hypothesis, there aren't really any applications of this in mathematical practice. So a lot of people say, well, that's not really relevant. It was like a really fascinating curiosity for mathematicians like Hilbert and others in the 1900, but why does anybody care? It doesn't. You can't prove anything in analysis from it, etc. But the axiom of choice comes up all the time. The axiom of choice is used to prove things like every vector space has a basis. In my linear algebra class, teaching people about things like that. It's used to prove that every field has an algebraic extension. There are a whole bunch of things that the axiom of choice can prove. And so we want to believe the axiom of choice. That's why we call it the axiom of choice. We take it as an axiom. Right? So we've accepted the axiom of choice to some extent as an additional axiom to ZF. And so what we have for formalizing mathematics, often we refer to ZFC because we throw in the axiom of choice. But in the case of the continuum hypothesis, nobody really knows what it, where it should go. Like, should it be accepted as true, or should it be contradicted? Is the size of the continuum, meaning the cardinality of the real numbers, really the next infinity after the size of the natural numbers, or is it one down, or is it further down? Gödel, who, like in his later years, did a lot of crazy things, he thought it was not the next one, but the one after that. And that sounds crazy, right? So if you know about Aleph numbers, this is Aleph 0, that side's there. The question is this Aleph 1? And Gödel said, no, I think it's Aleph 2. And a lot of people thought he was crazy for that. But there was sort of a revival of that idea about 20 years ago with some of the top set theorists in the community who gave an explanation of why they think the cardinality of the real numbers should be Aleph 2. Some people believe that over time, and Gödel thought this too, mathematicians will come to know our universe of sets better and better until they'll come to know and understand the cardinality of the reals, and they'll be able to answer this question not through proof, because we just showed that you can't prove it, but through our kind of conceptual understanding of the set universe. Other people think that's nuts. That's never going to happen. In some extreme cases, a mentor of mine at Stanford, he died a number of years ago, but he was somebody who worked a lot in this area. He said his conclusion was, this isn't even a coherent question. That there's something fundamentally flawed about our understanding of infinite sets that make it so that this question not only can't be answered, but as he put it, it's an indeterminate question. Well, that's the same thing, the same thing can't be answered, but there's no basis for us to make a decision about its truth. So I'm going to make sure I leave plenty of time for questions. And I've been doing a lot of talking, but not very much listening, so I want to listen to you guys too. I haven't, so I always have more to say than I write down, but I want to leave you with a few things to think about. One would be, I hope this is something that you at least find intriguing and, at least food for thought, if not a motivation for further exploration. There are lots of different ways that you can kind of dig into this more deeply, not just for your own, not necessarily as a direction of research, which is something I chose, but just for a further understanding about mathematical practice. Like I said at the beginning, I'm somebody who likes to think deeply about things that I do. A number of you have taken courses from me. People that have taken courses from me know that I often start off at the beginning having some kind of philosophical discussion about what is it that we're studying. What are the mathematical objects that are part of this course of study that we're about to undertake, and just try to get you to think about what you're doing a little bit more rather than just going through the motions. And the deeper you think about it, the more you kind of dig into these kinds of questions. So speaking of questions, I'm going to end there, and if you have any questions, I'm happy to stick around. So thank you very much for listening. You've been an attentive audience. And you can ask questions at any time. What is a set? You can ask me to draw a picture of the set universe. I'll do that. But yeah.
Did Gödel ever try to define any properties of Aleph 1, or his thoughts on Aleph 1?
Yeah, no, he definitely did, and I'm not expert on that. But I'll point out that the folks that we referred to from 20 years ago, their idea went something like this. They wanted to look at implications of the continuum hypothesis on other statements in mathematics, some of them kind of related to analysis, and they came up with, there was this whole chain of argument that they came up with, that they found statements that they want to believe are true, which is, that's what an axiom kind of is, and then finding a path to saying, well, if the continuum hypothesis, if the cardinality of the reals is Aleph 2, then that will have implications on these other statements. So there's some value you get by having a cardinality in between. And so they made that case. The names there, Hugh Wooden, he and I had we're academic brothers, as we say. We both have the same advisor. He's a big shot in set theory. He was at Berkeley for a long time. He's now at Harvard. And then John Steele at
Berkeley, these, and there were a few others, folks in other departments, that they made this strong case and then kind of retracted it. There's a great video of Hugh Wooden talking about that kind of path. It's intended for general audience. So his line of thinking that led him to that belief, and then why he was starting to think differently.
Do we know anything about the independence of the continuum hypothesis from ZFC and not just ZF?
Yeah, so it's those two they're not interconnected. So
Okay.
it's they're both independent of each other.
Okay.
Oh, wait a minute. No. Shoot, I said something wrong. Continuum hypothesis is independent of ZFC.
Okay.
But the other way, there's an implication of, I think, I should know this because I taught this before. I think you can use the generalized continuum hypothesis to prove the axiom of choice. I shouldn't say that without full context. Look that up. Homework exercise. Yes.
What are some other models of number theory?
Yeah, so I'll say briefly, and the idea is the following. So one of the big theorems of model theory is that any theory formalized in first order logic that has infinite models is going to have actually models of every infinite cardinality. So one thing that's interesting here is that this model is cardinality is accountably infinite. It's the same as the natural numbers. There are models of true arithmetic that are uncountable. That sounds bizarre. But the way we draw the model, the picture that I'm going to draw is the following. You have 0 and 1 and 2. Right? So this is our number line. And the points that we put into the natural numbers are we don't put in the in-between points. And this goes on as we think forever, and I represent that this way. So this is meant to capture the natural numbers. And so any model of piano arithmetic is going to include the natural numbers as we know them. But in order for it to be different, it has to include something else. And the only way that you can preserve truth and do that is by putting something else out here. So by the way, these are called non-standard models. And this is a very powerful tool, not just in logic, but in other parts of mathematics. It leads to something called non-standard analysis. And there's I could give a whole talk on this, but there's a way that you can capture the intuitions of Leibniz and Newton and Euler and all the analysts of the early days using a formalization of non-standard analysis that would correspond to what we sometimes call infinitesimal analysis. Anyway, this is a very useful thing. So you'd have at least one thing that lies away from these. A has the property it's greater than n for all the standard n, if you will. And then you have this thing out here. Now this number, A, it behaves like a natural number. It's either even or odd. You can double it. If it's even, you can take half of it. You can add 1 to it. So there are all these numbers. Like a plus 1 is out here, and there's a 2a out here. You won't get to 2a by adding 1 to a, right? So it's gonna keep going forever, and you never get to 2a because all you can do is add these standard n's, right? So and so this creates that, but you can also, given that a is not 0, there's an a minus 1, so it goes back like that. And there's a whole thing here I'm going to call a z chain. It's like a copy of the integers. But it turns out that there's a z chain around this one, and then there are numbers in between 2a and a that aren't accounted for here, so there's another z chain in between. And in fact, there's a whole density of z chains. So this model, I'm trying to describe something to you that's pretty abstract, but this non-standard model is going to include this whole kind of non-standard part that lies away from this. Now, here's the fascinating part of all this: is any fact that holds down here is going to hold in the whole thing. So if I write down something like, there exists an x that satisfies some polynomial equation, something like that. If this holds in the standard part, it holds in the non-standard parts. And I can do this I can pick my theory, and I can find non-standard models of a theory. A theory can be a theory that follows from the axioms, which I started off with before. So T could be some T of A, and I do that, but it could also be true arithmetic. So let me make this even more bizarre and interesting. If I take like the Gödel sentence, which says I am not provable, I can find a model where that holds, right? In that model, the proof of that sentence would need to be non-standard because there's no standard proof of it. So true arithmetic, the Gödel sentence, I'll write it this way, the sigma sub PA, the one says I am not provable. And down here, there's no code of a proof. But if I put a code of a proof up here, then I can make this false. And in that case, the resulting model would be a model of PA plus not this. And you could also have a model of PA plus that, right? Which we already believe this is true, so we think that down here there is no proof. But if we insert a proof, it has to be non-standard. So that's the kind of model theoretic approach to showing independence. I mean, this was my area of research, so I drew a lot of pictures. They don't correspond to anything in reality. It's just like a figment of my imagination. But I showed a lot of things are independent of PA and various other theories by doing this kind of model argument where I showed there's a model where the statement is true or the statement is false. And my favorite examples are with, well, I mentioned a couple of things, Paris-Harrington theorem, the Goodstein theorem, but the ones that I worked on personally had to do with functions of a very high growth rate. Oh, that could be another talk for another day. But you can have it so that a function, so if you think about exponentiation, that's a pretty steep function. You can think about iterating exponentiation and get a steeper one. How many of you have heard of Ackermann's function? A couple of you. You can go way beyond Ackermann's function. You can get these functions that are higher and higher growth rates. And Peano arithmetic can't prove programs for fast-growing functions terminate if those fast-growing functions grow too fast or too quickly. And so you can get out of reach. And then what ends up happening there is you find models where the value of the function lies outside of the range of the model. And so that's kind of the technique. Oh, I gave you too much information. That's a long answer to that question. Yeah.
Could you go into like the proof that Gödel had for like not, you can't disprove the continuum hypothesis?
Yeah, so, and I'm going to end there, and I'll stick around if there are more questions, but I see it's 5:45, so this will be my last one before we conclude. But I mentioned the cumulative hierarchy, so we draw it like this. So this is the set universe. If you take a course in set theory, including mine, but a lot of other people, this is how we draw the universe. Now this V represents kind of a building up of sets from earlier sets through a process. It has different stages. It's also V for von Neumann, because this is often von Neumann. I think I might have made that up. But in any case, we build out the set universe stages. And I can talk about ordinal numbers in these stages and where they go. And then, and part of the thing, my takeaway from the independence of the continuum hypothesis, axiom choice, and others, we don't have a lot of clarity about the set universe. I mean, we can describe it down here pretty well, where it's just finite. But once it gets into the infinite, it's harder and harder to grasp. And I'll point out, I mentioned that all of these different theories kind of live in the set universe. You can find a copy of the real numbers down here somewhere, and you can find, all of your manifolds a little higher up, and all kinds of things. But there isn't much up here that is relevant to mathematicians. Anyway, how do you prove that the continuum hypothesis is, how do you find a model where the continuum hypothesis is true? Gödel found a way of thinning this out, and he came up with something called L, which is sometimes referred to as Gödel's constructible universe. But constructible doesn't mean literally constructible, but it means that Gödel had a way of building up this universe with a restriction that made it so you're going to leave some sets out. And by leaving those sets out, it has some nice properties, including it satisfies the axiom choice and the continuum hypothesis. So this is a model of the truth. I'll point out that Cohen did the opposite. He showed how to fatten the universe up by adding more stuff. And so in particular, Cohen showed that you can extend the set theoretic universe to include new functions that map high cardinality sets onto the real numbers.
So I'll end there, but happy to answer more questions if there are any. Thanks again for listening.